A confidence interval refers to the probability that a population parameter will fall between a set of values for a certain proportion of times. So confidence intervals measure the degree of uncertainty or certainty in a sampling method. Confidence interval is a range of values bounded above and below the statistics mean that likely would contain an unknown population parameter. The confidence level refers to the percentage of probability or certainty that the confidence interval would contain the true population parameter when we draw a random sample many times. We use confidence intervals to measure uncertainty in a sample variable. For example, if we choose different samples randomly from the same population parameter and compute the confidence interval, if we continue this activity many times, the resulting intervals that we will get from the different data sets will be different each time. Some intervals might include the true population parameter and others might not. So a 95% confidence interval means that we are 95% certain the confidence interval would contain the true population parameter. Suppose we have collected n samples of data that we are interested in. Let's call that x. So we have data say from x1 to xn. Let's call the average of the data as x bar, which is equal to the sum of all x divided by n. Now suppose I calculate the sample variance of the x's. So sigma square will be given by 1 by n minus 1, then summation of xi minus x bar whole square. So from there, the confidence interval can be defined for a 95% confidence interval as given as x bar minus 1.96 into sigma by root n and x bar plus 1.96 sigma by root n. So this is for the 95% confidence interval. It's an interval that has a lower endpoint and an upper endpoint. So we can think of this as a master formula for the 95% interval. Similarly, we can calculate the confidence intervals for percentages other than 95 in general. Say for a gamma confidence interval, we have gamma confidence that the true population parameter will lie within that particular interval. From one of my previous videos, we found that intuitively there are two things that affect the confidence in an interval. You can check out that video. I'll put the link in the description if you haven't watched it. So in constructing a confidence interval, the first thing is the variance in the data. If the data is more spread out or has higher variance, then our confidence is less. Second, if we have more number of samples, then our confidence will be greater. So you see both these intuitions are reflected in the confidence interval. You can see that the width of the interval is proportional to sigma. That is, when the variance increases, so does the width of the confidence interval, because the confidence interval is wider. So we are actually less confident about our estimate. Secondly, we can see that the width of the interval is inversely proportional to square root of the number of samples. So when the sample size increases, the width of the confidence interval decreases. As the width of the confidence interval becomes smaller, our confidence in the estimate increases. So we can clearly see how this formula encapsulates the intuitions that we learned earlier. So higher variance leads to less confidence, while more samples leads to more confidence. Therefore, as the sample size increases, the range of interval values will narrow, which means that the mean we now know the mean with much more accuracy as compared with smaller sample. Suppose we are trying to find the population mean of a variable x. We have taken many samples and the sample mean of variable x is 4.27. Now after plotting the sample data and using 95% confidence interval, we get the upper and lower limit as 2.92 and 5.62 respectively. Now sometimes people often form this misconception regarding the confidence interval is that This 95% confidence interval represents the percentage of data from a given sample that falls between the upper and the lower bounds. Now, this is incorrect. The 95% confidence interval refers to 95% probability that this confidence interval would contain the true population mean of variable x. So confidence interval, as we see, provide more information than just the point estimates. By establishing a 95% confidence interval using the sample means and standard deviation, and we assume a normal distribution represented by the bell curve, we can arrive at an upper bound and lower bound that might contain the true mean 95% of the time. So the 95% confidence interval is a range of values that we can be 95% confident about that it will contain the true mean of the population. So due to natural sampling variability, sample mean of the center of the confidence interval will vary from sample to sample. So we can see that the confidence is in the method, not in a particular confidence interval.